So we were studying about transfer functions, and we have seen how to solve circuit using the Laplace transform. Let us try to do a problem today. So suppose this is a network, electrical network. It has these 4 nodes. So suppose someone, let us assume the question says that we have a current source applied between nodes A, B. There is a current source I1t which is equal to ut, and the question says find h of s is equal to VCD over I1. This obviously is in the S domain, both values. This is in the time domain. This circuit in the time domain, and here we are interested in this voltage across this resistor, and there is a current source between AB, and it is entering entering node A, so it is directed upwards. Although we, in order to find h of s, we do not specifically need any specific I1. Whether it is ut or some other input current, we can still get the same value of hs, because we are going to take the ratio of this voltage to this current. So here you can see that the transfer function is a ratio of voltage and current. So in a way, basically this would have units of impedance, because this is voltage over current. So this transfer function is going to have units of impedance. If the transfer function is a ratio between v's or i's, v over v or I over I, then it is dimensionless. But if the transfer function is between a ratio of v to I, then it has the units of the impedance, and if it is between I and v, then it has the units of admittance. So how would we solve this? We will convert the circuit to its frequency domain equivalent. And obviously we have a current I1 coming in from here, and this will become 1 over Cs, which is going to be 0.1 S and 300 and 200. Where this voltage is VCD. Then in order to find this voltage, we can make use of the node voltage method and try to solve it, or we can use the current divider method and find this current that is going to flow. This is open, nothing is connected here, and we know there is a voltage current source connected here. We can actually draw it, and then we know that this I1 is actually ut, and the Laplace transform of ut is 1 over s. So we know the Laplace transform of I1t is 1 over s, and we have to find this VCD, for this particular I1. So let us try to solve this using the node voltage method. This is not the only method to solve it. We can in fact do a source transformation here, and a current source parallel with this resistor can be converted to a voltage source in series with this resistor, and then we can probably solve this using the voltage divider method. But let us stick with that. So we know this is VCD. Let us call this voltage to be V1. Then V1, this outward current is minus I1 plus V1 minus VCD over 10 over S, 1 over 0.1 is 10, plus V1 over 300 is equal to 0, and VCD minus V1 over 10 over S plus VCD over 200 is equal to 0. I have just kept this VCD, although this is not an essential node because no current is going here. This is not an essential node. We can actually just solve it for one node V1, and this current, outward current, would be V1 minus 0 divided by 10 over S plus 200. But in fact, once we have found V1, we would need to find VCD through the application of voltage divider or similar technique. So that would essentially be the same thing. So from these equations, one of these equations, we can find what V1 is and then apply it to the other one. So here we don't have I1 in that, but here we have I1 and VCD as well. So in order to find their ratio, we can find what V1 is from here. So we can see that this is S VCD over 10 plus VCD over 200 is equal to V1 S V1 over 10. So we can multiply throughout by 200 to get 20 S V1 is equal to 20 S VCD plus VCD, and V1 is equal to VCD 20S plus 1 divided by 20S. And we can put this V1 in this equation, and this equation is going to give us minus I1 plus V1 S over 10 plus 1 over 300 minus S VCD over 10 is equal to 0, minus I1 plus VCD, by putting what V1 is, into 20S plus 1 over 20S. We can take the LCM to be 300, and then we have 30S plus 1 minus S VCD over 10 is equal to 0. So let us simplify this. We are going to get I1 is equal to VCD common and 20S plus 1, 30S plus 1 divided by 6000 S minus S by 10. So let us simplify this thing. 6000 S 20S plus 1, 30S plus 1 minus 600S. Here we can see, okay, let us expand this. We are going to get 600 s square, and then this 20s, this 30s plus 50s plus 1 minus 600 s square over 6000 s VCD I1 . So we get 50s plus 1 over 6000 s is equal to I1 over VCD. You see, we have not used what I1 is, 1 over s. We don't need that because we are interested in finding a ratio, and therefore VCD over I1 is 6000 s over 50 s plus 1. I think I have made a mistake somewhere, and that mistake shouldn't have been made. This is in microfarad. I have skipped doing this. So we basically have into 10 raised to the power minus 6 here. So it is not 10, it is 10 raised to the power 7 here. So we need to solve this thoroughly, but just in order to make the minimum changes to correct what I have done, let us consider that this is 0.1 farad, capacitor of 0.1 farad. So now we can write this as 120 s over s plus 1 over 50. I think 1 over 50 would be 0.02. So this is the transfer function that we had been looking for. I think if you take the value of the capacitor to be 0.1 microfarad, this solves up to be 120 s over s plus 20,000. You can verify that. And this is how you solve circuit for transfer function. Let me just re-emphasize once again that the network must not have any source of energy in order to find transfer function. No initial conditions, no independent source. So for any circuit, it is very important to note this very important point. And if you are interested in finding the transfer function h of s for any network, the capacitors and inductors should not have any stored energy, and there should not be any voltage source or independent current source contained in the circuit as well. That is very important. So if the question would have been to find VCD, then obviously that would be equal to I1 into h of s. And here this I1, the Laplace transform of ut is 1 over s into 120 s over s plus 0.02. So you would have gotten 120 over s plus 0.02. So this basically tells about the nature of the circuit. look at the pole. The pole is there. The same pole is there in the output. It is there because of the nature of the circuit, and it is there in the output as well. So, and just reminding you about zeros and poles. So what are the zeros and poles of this transfer function? So zeros are at s is equal to 0 only, the roots of the numerator, and the poles are, there is only a single factor, a linear factor in the denominator. So at s is equal to minus 0.02, there is one pole. There is also a 0 at s is equal to infinity. Now in this case there isn't any pole at s is equal to infinity. Why? Because when s is very large, this s and this term will cancel and it's just a constant, there is no 0. So if we need to draw a pole 0 diagram in the s plane, then we have a 0 here at the origin and a pole at minus 0.02. This is the j omega axis and this is the sigma axis. Sigma is the real value. Remember, s is a complex frequency that is equal to sigma plus j omega. This is the radian frequency. This is the attenuation factor. So this is how things are. Just trying to sum up all the things we have learned up till now.